So now we'll talk about some real-world examples where we might be able to use this concept of tree. So first of all, there's game trees. So this picture here represents the first 3 layers of the game tree of tic-tac-toe. If you remember how tic-tac-toe is played, there's 9 boxes, start out empty, and then let's say that X gets to go first. There's 2 players. One draws X's in the boxes, the other draws O's. So let's say X goes first. So we see that this first, after the root, then that first, the next layer there, we've got 3 possibilities. Now you might think there should be 9 possibilities there because there's 9 boxes, but the one on the left, which on this second level, where we just have the X by itself to the top left, that could actually represent any of the corners, because all we would have to do is just flip the box, or rotate it around, and we would be showing any of those corners. So we can get by with just showing 1 in one corner and know that that would represent any of the corners. Then in the middle one on that second layer would be just if the player X put their mark right there in the middle. And then the next one is where maybe instead X would put the X not in a corner, not in the middle, but on one of those others. And so again, that is just one picture, but it could represent all of the possibilities. We could rotate that around. Okay, so really we would only need to show 3 of these configurations for the first play of the game, where X, the player X puts an X in one of the boxes. Then we can go on to another layer, which would show all of the possibilities for what could happen next. So if you follow this this first box on the second layer down and see what all the possibilities are past that, you see that in all of these cases X is at the top left, again representing that it's at some corner, and we could flip it around and it could be on another corner. But then here's all the possibilities for where that second player could put the O. And if you take a look at that, we won't talk about every one, but if you take a look at that, you can realize that each of those could represent more than one. So for instance, well, most of those could represent more than one. The first one, far left on this bottom level, that could represent where the second player put an O on either this top right where it's showing now, or the bottom left. So that could represent 2 plays. Here on the second box in the final layer, there'd only be one option there, and that's where we put the O diagonal from the X. Anyway, so you can kind of take a look and you could realize that all of those possibilities there could represent the different plays that O could take. And then those there would just be coming off of that first option for X, but then X also, the player X could have put the X in the middle, and so these would be options for that. And so anyway, you can kind of see that this tree would show all of the possibilities that could happen in the first two plays of the game, right? When X puts their first one in, and then O puts one in. So you can imagine that this could get very big very quick, because this is only just one turn for each, and so it would get very big. But we could consider these plays as a tree. Now what would happen is would go on, this tree would continue on and on and on until, and imagine that the scenarios where somebody would finally win, right? So when somebody would win, get all of the X's in a row or all of the O's in a row, then there would be no more gameplay after that. So that would represent a leaf, because there'd be no more plays after that. So a leaf vertex in the tree would represent a configuration for when the game would be over. And as I've said, in practice, for most games, this tree is much too large to build and analyze in its entirety. But it is a possibility. And you can imagine in a scenario where the computer is keeping track of this, it wouldn't be too difficult for a computer to keep track of all of this. So in Zybooks, you have some problems to do where they give you a configuration for tic-tac-toe, and you're supposed to write down the children of each configuration. And then it says indicate which children are leaves and the outcome of the game. I don't know if we'll get that far. I have just part A and part B. We'll see if any of the children of each of these, part A and B, would end up being that represent leaves. So we'll see. So let's just look at part A here. So it says that here's the configuration now, and it says it's O's turn to play next. So in this case, you can tell then it would have been that the player that puts the O's would have been the one that go first, right? Because they each have 3. So turns out, I guess, that would have been the case, that O got to go first, and so now there's 3 of each, and now it's O's turn to play. So write down the children of each of those. So imagine here that this is this initial configuration, and now that is, we've got some edges coming out of that vertex, and we're going to see what are the possibilities. So what would that be? Well, there's really 3 possibilities here. They could have put the O at the top right, the O in the middle, or the O not in the top right or the middle, but the one the other one left. Okay, so there's just 3 possibilities there. So yeah, I guess we could say which are leaves. This first one here on the left, that would be a leaf because O has won the game. The second one also would be a leaf because O has won the game. But this third one here, no one has won yet. So on part B, they give us this, and they tell us that it's it's X's turn to play next. So again, imagine what they gave us as the vertex, and we're looking for the children there. So we could say, well, X could go any of these 3 slots that are left. So we could put those there. And then which of those would be leaves? That the middle one would be a leaf because X has won. So that would be a leaf. Okay. The next application has to do with storing text files in the most efficient way as far as space is concerned. So first of all, let's think about how text files are stored. On computers, they're stored as binary strings, as we would expect. Each character would be assigned some certain binary code, and then usually by the ASCII, using the ASCII table or the Unicode table. So every character has its own binary code, and in general, the standard way to do it is that each of these characters has a fixed length for its binary string. So ASCII and Unicode, if we're using those values, then every character would have the same length of a binary string that would represent that character. Okay, but now it might be more efficient if we could have different characters be represented by different lengths of binary strings, right? Because some characters are used more often than others. If we could get those characters that are used more often than others to be able to be stored with a shorter binary string than some of these ones that we rarely see, like a Z or something, then the space could be saved in general, right? So that's the idea here, that we'd want to come up with a way to somehow represent these different characters by binary strings, but have it so that characters like A and E would need fewer binary digits, fewer bits, while characters like Z or Q would have more bits. So is there a way to do that? Well, we can do that, and there's a certain kind of code called a prefix code, and we'll talk in a minute about why it's called prefix code. But let's say that we come up with a tree. Here's just a very simple tree. It doesn't include all of the letters in the alphabet, just includes some. But let's say that this is just a very small little example of what we could do, and you could imagine that you could come up with a tree that would have a lot more than just these 6 characters here. But let's say that we have this, and we come up with a tree like this, and we have 2 edges, or we might call them branches, coming out of each vertex. And sometimes when we have an edge coming out, sometimes it ends up as a letter, like here we have A, E, C, N, D, Y. But sometimes we see another vertex, and then there's 2 more branches that come out of that. So here we see that we've got on each of these branches, it's labeled either a 0 or a 1. So if we had something that looked like this, and we wanted to encode the word day, D-A-Y, using this tree, let's see how we would do that. We'd say, well, let's find the D. The D is down here at the bottom. So to get to D, what would we have needed to do? We would have needed to start at the root and go along the edge that's labeled 1, go along the next branch that's labeled 1, go along one more branch labeled 1, and then when we get down to almost the bottom, we see then that we would need to follow that edge labeled 0 to get to the D. So for the letter D, we would use 1, 1, 1, 0. That would get us down to the D. Now to get to the A, we would just have to start at the top and then just go 0, and then we're already at A. Y would be, to get to the Y, we have to go 1, 1, 1, 1. So we'd have 4 ones there. So we could encode this word day by using this little scheme here, using this tree. And notice that A, which is a common letter that could be used quite often if you have a longer string, just a sentence or something, A is used a lot in the English alphabet, so that might show up a lot. Notice A can be encoded just by 1 little digit, whereas we did need 4 digits for the Y and 4 digits for the D, but those aren't as common. Let's encode the word candy. So we have these different letters here. First, let's look for the C. We need to go 1, 1, 0, 0 to get to the C. The A again is just a 0. The N would be 1, 1, 0, 1. D, we need to go 1, 1, 1, 0. And Y would be 1, 1, 1, 1. Okay, so yeah. So that would be how we can code candy. And the last one, let's decode something. Let's take this here, this long binary string, and see if we can come up with letters for it. And you might be wondering, how can this even work? How do we know of these, when we start working with these digits here, how do we know that we're done with a letter? And how do we, because some letters take 1 bit, some letters take more. So you might be thinking, how can we go backwards on this? But it turns out the way we're doing this here, we can, because you would just keep going until you find a letter. So I see a 1, 1, 1, and so I could go on this tree 1, 1, 1. I'm not to a letter yet. So I keep going 1, 1, 1, 0, 1, 1, 1, 0. Okay? If I go 1, 1, 1, 0, I see that I've arrived at a letter. So I would know that that would represent that those first 4 represents the letter D. Then I go on, I have a 1 and a 0. If I go 1, 0, I see I'm already at a letter, and that's E. So that I would get an E for those next 2 digits. And the last 4 digits, 1, 1, 0, 1, 1, 1, 0, 1, we get down to the letter N. So we'd have N. So that binary string would convert into the word den. So this works pretty well, and as you can see, we can use variable length codes, and so we could set it up just right so that those more common letters that are used, a lot more often can have shorter codes associated with them. Now, why is this called a prefix code? So this was the example that we just did. It's because that the code for one character is never going to be a prefix for another character, okay? Because remember we said we knew to stop when we got all the way down to a character. So basically, I guess you could put it this way. In our tree, each letter is at the end of a path, right? We never are going to continue on after a letter. So that makes every letter's code not be able to be a prefix of another letter, because if it was a prefix of another letter, we would have to be continuing on this tree past a letter, and once we come up to a letter, then we're always stopping. So prefix code has the property that the code for one character cannot be a prefix of the code for another. The fact that the codes are organized as a tree in which characters are only stored at the leaves ensures that this is true. Okay, so that's why it's called a prefix code. In a sense, it's called a prefix code because no letter's code is a prefix of any other letter. So here's just an example. The code for A is O1. No, that's not in our table here. I mean, in our tree, I was looking up at this tree that we have up here, and that is not the code for A, right? The code for A would just be a 0. But this is just an example for some other tree, let's say. So let's say we have another tree, and if the code for A is 0, 1, and the code for B is 0, 1, 1, 0, then that's where we'd have a problem. So that's why we don't have a tree up here that's got this particular situation, right? Because 01 would be the code for A, but that would be a prefix for B because it starts with 01, and then we have some other characters after it. That's when it'd be a problem, right? Because then it'd be ambiguous. Is that 01, does that stand for A, or is that just the first part of B? So the decoder, wouldn't know whether that's an A or if we're just on our way to getting a B. So that would be the case where one letter is a prefix for another letter. One letter's code is a prefix for another letter's code, and that's when we couldn't decode, right, because of that. So this would be an example here where we would not consider this a prefix code because we could not decode like we have. So those are just 2 applications of trees, and you could maybe come up with some others if you thought about it. I think Zybooks only covers these 2 types of applications to trees.